Good morning, guys. What's up? Um, Give me 1 second to make sure that this video is working. I just need to go to YouTube and then I gotta post it somewhere. What? Part one? Oh no. Give me 1 second. Sorry, I'm just looking for here it is. Okay, I just want to post this somewhere and then we're gonna start. This is part two of proving that the earth is round to these stupid people who are in the alt-right that are saying that it is like flat or some kind of junk like that. And I don't know why this is happening. I think that I actually told you before I was talking to Chat GPT and I asked her, I'm like, I was talking to her about talking to the alt-right and I asked her, I was like, is flat earth like a phenomenon going on in the flat and the alt-right now? And she said, yes, it is to a certain degree. There's a degree of flat earth propaganda going on in the alt-right. And I was like, why would anyone like just basically do this? And I actually forget her answer. I was like, why would anyone just subscribe to such an outlandish conspiracy theory and like make their thing look bad? And I think both her and Jord had the same answer, in that it is like a total dismissal of mainstream. It's a total rebellion against the mainstream. Like, we don't even believe your science. You know what I mean? It's just to like just the ultimate rebellion. We don't even believe your science. But I think that's really stupid. I think it's stupid to rebel on everything. I think it's stupid to rebel on everything. Like, you have to admit when the other side has merits. Like, okay, like the system that I promote is Beyondism, right? Religionofbeyondism.blogspot.com. Religionofbeyondism.blogspot.com. You can find the books, the manifesto, the chapter summaries, everything all right there. So basically in Beyondism, you're supposed to steal your other people's merits, right? You're supposed to steal their genes that are good, and you're supposed to steal their ideas and cultural aspects that are good. So, okay, the other side, if you're in the alt-right, has some pretty good science. I know you're going to say, oh, well, what about gender? The gender, they don't get it right on gender and they don't get it right. Or some of you might say things like vaccines. Some of you might say things like climate change and stuff like that, or whatever your particular thing is. But I'm not going to deny that the other side misuses science. I'm not going to say that, but there is science that is settled, whether you're on the left or the right, and there is science that the left uses that is sound, like astronomy, to prove that the earth is round. Because most of the people that are saying the earth is flat, a lot of them, not all of them, a lot of them do come from like a Christian perspective. I know a lot of them, it's very important to their theology and to their worldview for humans to be the center of the universe. Yeah, it is important for them. So steal it. Don't just fight against it. Actually, if you give me a second, let me make some coffee. Hold on. Give me 1 second. We're going to review a little bit of yesterday because I didn't have the proper screen on. Sorry, just give me 1 second. Okay. Just to review quickly yesterday what we did. Okay, so if you go to Bruno's blog m.blogspot.com, BRUNOSBLOGM.blogspot.com. Come to the October 20th, 2023 post. You will see the two essays I wrote on the Earth being round. Yesterday, what we went through is so people have the flat earthers say, why don't birds when they fly fall behind the Earth? And that is because so they're on the Earth and they're going at the speed of the Earth, and then when they fly off the Earth, they're still going at the speed of the Earth, right? They're still going at the speed of the Earth. So, and also, why don't people fly off the Earth? It's because you're going on a tangent. We learned that Mars and Venus at the time, even at Galileo's time, could be seen to be going around the sun. We also saw that they could tell that so other planets were going around the sun. So why not Earth? And then there were moons going around Jupiter. So if not everything is revolving around the Earth, then the Earth is not the center of the universe. I mean, Jupiter is the center of those moons. They're not the moons of Jupiter. They're not going around the Earth, and that could be seen in a telescope. So even in Galileo's time, before space, or I mean, long before all the modern types of science that we had, it became obvious to a certain degree that the Earth was round. Okay, and then oh wait, where am I? How did that happen? Oh, odd. Okay, and then unfortunately the other day I didn't show any of this, but there were the laws of planetary motion. There was Tycho Brahe and Kepler, Johannes Kepler, and okay, so basically we were showing that what are the three laws? The three laws are: first law, each planet moves around the sun in an orbit that is an ellipse with the sun at one focus of the ellipse. So we learned here that the planetary motion that goes around the sun is not circular, it's elliptical. Okay, it's elliptical. And let's see what's the other planetary Kepler's second law: the straight line joining a planet and the sun sweeps out equal areas in space in equal intervals. So here it is, like you can see as it goes around, that's an equal area in space, and this is an equal area in space. So when it's closer to the sun, it covers more area of space. When it's farther from the sun, it would cover more in the same period, because you can see this yellow is the same as this yellow. And Kepler's third law: the square of a planet's orbital period is directly proportional to the cube of the semi-major axis of the orbital. So we can see that there's a certain kind of symmetry and geometry going on that is visible. So the thing is that flat earthers, so we have an explanation, right? We have an explanation. We see something in the sky and we observe it and we build a model like this. We build a model, and then the mathematical proportions all equal each other if our model is correct. So we say, okay, here's our model, and if this is our model, then we would predict this, 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 and this. And it starts to come true. And we're not even at the point where we're really making major predictions yet. I think this is still theory, though there might have been a certain degree. Okay, this might all be theory, but these theories are going to be leading to predictions that we can predict when the tides are going to happen, when an eclipse is going to happen, when that's going to happen, where the stars are going to be, where the moon is going to be, what phase the moon will be in, that kind of stuff. And we can, tell that kind of thing. So let's go into chapter 3.2, which is Newton's great synthesis. So if you give me a second, let me just get my coffee. Okay. Got my coffee. Okay, let's continue. Okay. It was the genius of Isaac Newton that found a conceptual framework that completely explained the observations and rules assembled by Galileo, Braque, Kepler, and others. Galileo, Braque, Kepler, and others. Newton was born in Lincolnshire, England, in the year that Galileo's death, against the advice of his mother, who wanted him to stay home and help with the family farm. He entered Trinity College at Cambridge in 1661, and 8 years later was appointed professor of mathematics. Among Newton's contemporaries in England were architect Christopher Wren, author Alfred Ben, and Daniel Defoe, and composer G.A.F. Handel. Newton's law of motion. As a young man in college, Newton became interested in natural philosophy, as science was then called. He worked out some of his first ideas on machines and optics during the plague year of 1865 to 1866, when students were sent home from college. Newton, a moody and often difficult man, continued to work on his ideas in private, even inventing new mathematical tools to help him deal with the complexities involved. Eventually, his friend Edmund Halley prevailed on him to collect and publish the results of his remarkable investigation on motion and gravity. The result was a volume that set out the underlying system of the physical world, Philosophia Naturalis Principia Mathematica. The Principia, as the book is generally known, was published at Halley's expense in 1687. At the very beginning, the Principia, Newton proposed 3 laws that would govern the motion of all objects. Newton's first law: every object will continue to be in a state of rest or move at a constant speed in a straight line unless it is compelled to change by an outside force. Newton's second law: the change of motion of a body is proportional to and in the direction of the force acting on it. Newton's third law: for every action, there is an equal and opposite reaction, or the mutual action of 2 bodies upon each other are always equal and act in opposite directions. In the original Latin, the 3 laws contain only 59 words, but those few words set the stage for modern science. Let us examine them more carefully. Interpretation of Newton's laws. Newton's first law is a restatement of one of Galileo's discoveries, called the conservation of momentum. The law states that the absence of any outside influence, there is a measure of a body's motion called its momentum that remains unchanged. Yet you may have heard the term momentum used in everyday expressions, such as the bill is in Congress. This bill in Congress has a lot of momentum. It's going to be hard to stop. Newton's first law is sometimes called the law of inertia, where inertia is the tendency of object and legislature to keep doing what they are already doing. In other words, a stationary object stays put and the moving object keeps moving unless some other force intervenes. Let's define the precise meaning of momentum. It depends on 3 factors. 1, speed, how fast a body moves. 0, if it is stationary. 2, the direction of its motion. And 3, its mass, a measure of the amount of matter in a body, which we will discuss later. I was talking to these flat earthers, and they were even getting to the point that they were saying, well, what is mass? We don't even know what mass is. Mass is the amount of matter, or it was either mass or matter. Matter. Maybe it was, no, they used the word mass, but what they were really probably meaning is what is matter, because mass is just matter per volume, amount of matter per volume, right? In a certain space. And so they probably were meaning, well, how do we know what matter is? And matter is obviously what is observable and weighable. What's there if there's nothing there? They try to draw you into these conversations where they're saying, well, we don't know what anything is. We don't understand anything. And to a certain degree, we do understand things. We understand measurement and we understand what those measurements mean, and we can measure matter. Scientists use the term velocity to describe the speed and direction of motion. For example, 20 kilometers per hour due south is velocity, whereas 20 kilometers per hour just by itself is speed. Momentum that can be directed as an object mass times its velocity. It's not so easy to see the rules in action in the everyday world because many forces acting on a body at any one time. One important force is friction, which generally slows things down. If you roll a ball along the sidewalk, it eventually comes to a stop because the sidewalk exerts a rubbering force on the ball. But in the space between the stars, there is so little matter that friction is insignificant. Objects can, in fact, continue to move to coast indefinitely. Momentum of body can change only under the action of an outside influence. Newton's second law expresses force in terms of its ability to change momentum with time. A force, a push, or a pull has both side and direction. When a force is applied to a body, the momentum change in the direction of the applied force. This means that a force is required to change either the speed or the direction of the body. That is to start it moving, its speed up, to slow it down, to stop it, or to change its direction. As you learned in observing the sky, birth of astronomy, the rate of change in an object's velocity is called acceleration. Newton showed that the acceleration of a body was proportional to the force being applied to it. Suppose that after a long period of reading, you push an astronomy book away from you on a long, smooth table. We use a smooth table so we can ignore friction. If you push the book steadily, it will continue to speed up as long as you are pushing it. The harder you push the book, the larger its acceleration will be. How much of a force will accelerate an object is also determined by the object's mass. If you kept pushing a pen with the same force with which you push the textbook, the pen, having less mass, would be accelerated to a greater speed. Newton's third law is perhaps the most profound of the rules he discovered. Basically, it is the generalization of the first law, but it also gives a way to define its mass. If we consider a system of two or more objects isolated from outside influence, Newton's first law says that the total momentum of the object should remain constant. Therefore, any change of momentum within the system must be balanced by another change that is equal and opposite so that the momentum of the entire system is not changed. This means that the forces in nature do not occur alone. We find that in situation there is always a pair of forces that are equal and opposite to each other. If a force is exerted on an object, it must be exerted by something else, and the object will exert an equal and opposite force back on that something. We can look at a simple example to demonstrate this. Suppose that the daredevil astronomy student, an avid skateboarder, wants to jump from his secondary story dorm window onto his board below. We don't recommend trying this. The force pulling him down after jumping, as we will see in the next section, is the force of gravity between him and the earth. Both he and earth must experience the same total change of momentum because the influence of these mutual forces. So both the student of earth are accelerated by each other's pull. However, the student does much more of the moving because earth has enormously greater mass. It can experience the same change of momentum by accelerating only a very small amount. Things fall towards earth all the time, but the acceleration of our planet as a result is far too small to be measured. A more obvious example of the mutual nature of the force between the objects is similar to who have battled a baseball. The recoil you feel as you swing your bat shows that the ball exerts a force on it during the impact, just as the bat does on the ball. Similarly, when a rifle you are bracing on your shoulder is discharged, the force pushing the bullet out of the muzzle is equal to the force pushing back upon the gun and your shoulder. This is the principle behind jet engines and rockets. The force that discharges the exhaust gases from the rear of the rocket is accompanied by the force that pushes the rocket forward. The exhaust gases need not push against air or earth's. A rocket actually operates best in a vacuum. Okay, mass, volume, and density. Okay, now let's talk about mass, volume, and density because this thing, mass, doesn't exist. Before we go on to discuss Newton's other words, we want to take a brief look at some terms that will be important to sort out clearly. We begin with mass. which is a measure of the amount of material within an object. The volume of an object is the measure of the physical space it occupies. Volume is measured in cubic units such as cubic centimeters or liters. The volume is the size of an object. A penny and an inflated balloon maybe both have the same mass, but they have very different volumes. The reason is that they also have a very different densities, which is a measure of how much mass there is per unit volume. Specific density is the mass divided by the volume. Note that in everyday language, we often use heavy and light as indicated by density rather than weight. As for instance, when we say that iron is heavy or that whipped cream is light. The unit density that we will be used in this book are grams per cubic centimeter. If a block of some material has mass of 300 grams and volume of 100 centimeters, its density is 3 grams per centimeter cubed. Similarly, materials span a considerable range in density from artificial materials such as plastic, insulating foam less than 0.1 grams per centimeter cubed to gold, which is 19.3 grams per centimeter cubed, gives the densities of some similar. Table 3.1 gives the densities of some familiar objects in the astronomical universe. Much more remarkable densities can be found all the way from a comet's tail, 10 to negative 16th grams per centimeter cubed, to a collapsed star collapse called a neutron star, which is 10 to the 15 grams per centimeter cubed. So, excuse me, here are some densities. We don't need to go over those. Angular momentum. A concept that is I think, yeah, this was what people were trying to say, like, why don't people fall off? Or I think this has to do with the concept that is a bit more complex but important to understanding many astronomical objects is angular momentum, which is a measure of rotation of a body as it revolves around some fixed point. An example is a planet orbiting the sun. The angular momentum of an object is defined as the product of its mass, its velocity, and its distance from the fixed point around which it evolves. In these three quantities remain constant. There is if motion of a particular object takes place at a constant velocity at a fixed distance from the spin center, then the angular momentum is also constant. Kepler's second law is a consequence of conservation of angular momentum. As a planet approaches the sun on its elliptical orbit and the distance to the spin center decreases, the planet speeds up to conserve the angular momentum. Similarly, when the planet is farther from the sun, it moves more slowly. Okay, this was about why planets move more quickly when they are close to the sun, or maybe when they're closer to the sun or further from the sun, they move more quickly. Similarly, when the planet is farther from the sun, it moves more slowly. So when it's close to the sun, it moves more quickly. The conservative of angular momentum is illustrated by a figure skater who brings their arms and legs in to spin more rapidly and extends their arms to slow down. You can duplicate this yourself on a well-oiled swivel stool by starting yourself spinning slowly with your arms extended and then pulling your arms in. And another example of the conservative of angular momentum is a shrinking cloud of dust or a star collapsing on itself. Both are situations that you will learn about as you read on. As material moves to a lesser distance from the spin center, the speed of the material increases to conserve angular momentum. Okay. Newton's universal laws of gravitation. Newton's laws of motion show that objects are at rest will stay at rest, and those in motion will continue moving only uniformly in a straight line unless acted upon by force. Thus, it is the straightest line that defines the most natural state of motion, but the planet moves in ellipses, not straight lines. Therefore, some forces must be bending their paths. That force Newton proposed was gravity. In Newton's time, gravity was something associated with Earth alone. Everyday experience shows us that Earth exerts a gravitational force upon an object at its surface. If you drop something, it accelerates towards Earth as it falls. Newton's insight was that Earth's gravity might extend as far as the moon and produce the force required to curve the moon's path from a straight line and keep it in orbit. He further hypothesized that gravity is not limited to Earth, but there is a general force of attraction between all material bodies. If so, the attractive force between the sun and each of the planets
could keep them in orbit. This may seem part of the everyday thinking, but it was remarkable insight in Newton's time. Once Newton boldly hypothesized that there was a universal attraction among all bodies, whereas in space he had to determine the exact nature of the attraction. The precise mathematical description of the gravitational force had to dictate that the planets most exactly as Kepler's had described them. The precise mathematical description of the gravitational forces had to dictate that the planets most exactly as Kepler had described them to, as expressed in Kepler's three laws. Also, that gravitational force had to predict the correct behavior of falling bodies on Earth as observed by Galileo. However, must the force of gravity depend on distance in order for these conditions to be met? The answer of this question requires the mathematical tools that had not yet been developed, but did not deter Isaac Newton, who invented what we today call calculus to deal with this problem. Eventually, he was able to conclude that the magnitude of the force of gravity must decrease with increasing distance between the sun and the planets or between any objects in proportion to the universe's square of their separation. In other words, if a planet were twice as far from the sun, the force would be 1/2 squared or 1/4 as large. But the planet 3 times farther away from the sun would be 1/3 squared or 1/9 as large. Newton also concluded that the gravitational attraction between two bodies must be proportional to their masses. The more mass an object has, the stronger the pull of its gravitational force. The gravitational attraction between any two objects is therefore given by one of the most famous equations in all of science. Force of gravity equals G, which is gravity times mass 1 times mass q square 2 over R, which I think is separation, where F gravity is the gravitational force between objects M1 and M2 are the masses of the two objects, and R is their separation. G is a constant number known as the universal gravitational constant, and the gravitation itself symbolically symbolizes Newton's universal law of gravitation. With such a force and the laws of motion, Newton was able to show mathematically that the only orbits permitted were exactly those described by Kepler's law. Newton's universe. Okay, so Kepler's law was the only type that could exist, right? Newton's universal law of gravitation works from the planets, but it's really universal. The gravitational theory would also predict the observed acceleration of the moon toward Earth as it orbits Earth, as well as any object, say an apple, dropped near Earth's surface. The falling of the apple is something we can measure quite easily, but can we use it to predict the motion of the moon? Recall that according to Newton's second law, forces cause an acceleration. Newton's universal law of gravitation says that the force acting upon and therefore the acceleration of an object toward Earth must be inversely proportional to the square of its distance from the center of the Earth. Objects like apples of the surface of the Earth at a distance 1 Earth radius from the center of the Earth are observed to accelerate downward at 9.8 meters per second or 9.8 meters per second squared. It is this force of gravity on the surface of gravity that gives us our sense of weight. Unlike your mass, which would remain the same at any planet or moon, your weight depends on the local force of gravity. So you would weigh less on Mars and Moon than on Earth, even though there is no change in your mass, which means you will still have to go easy on desserts in the college cafeteria when you go back. The moon is 60 Earth radii away from the center of the Earth. If gravity and the acceleration it causes gets weaker with distance squared, the acceleration the moon experiences should be a lot less than for the apple. The acceleration should be 1/60th squared or 1/3600 or 3,600 times less, or about 0.00272 meters per second squared. This is precisely the observed acceleration of the moon in its orbit. As we shall see, the moon does not fall to Earth with the acceleration, but falls around Earth. Imagine the thrill Newton must have felt to realize he had discovered and verified a law that holds the Earth, apples, and moon as far as he knew everything in the universe. Gravity is a built-in property of the mass. Whenever there are masses in the universe, they will interact via the forces of gravitational attraction. The more mass there is, the greater the force of attraction. Here on Earth, the largest construction of mass is, of course, the planet we stand on, and its pull dominates the gravitational interaction we experience. But everything with mass attracts everything else with mass anywhere in the universe. Newton's law also implies that gravity near never becomes zero. It quickly becomes weaker with distance, but it continues to act to some degree no matter how far you get. The pull of the sun is stronger at Mercury than at Pluto, but it can be felt far beyond Pluto, where astronomers have good evidence that it continuously makes enormous numbers of small icy bodies move around huge orbits, and the sun gravitational pulls join with the pull of billions of other stars to create the gravitational pull of the Milky Way galaxy. That force in turn can make other smaller galaxies orbits around the Milky Way and go on. Why is it then, you must ask, that the astronauts aboard the space shuttle appear to have no gravitational force acting upon them when we see images on television of astronauts and objects floating in the spacecraft? After the astronauts in the shuttle are only a few hundred kilometers above the surface of the Earth, which is not a significant distance compared to the size of the Earth, so gravity is certainly not a great deal weaker than much farther away. The astronauts feel weightless means that they don't feel the gravitational force acting on them, for the same reason that passengers in an elevator whose cable has broken or on an airplane whose engines no longer work feel weightless. They are falling. Okay, so well, when falling, they are in free fall and accelerate at the same rate as everything around them, including their space or camera, which when they are taking photos of the Earth. When doing so, astronauts experience no additional force and therefore feel weightless. Unlike the falling elevator passengers, however, the astronauts are falling around the Earth, not to the Earth. As a result, they will continue to fall and raise to be in orbit around the Earth. Okay. See the next section for more on orbits. Okay, so that's a good thing to talk to flat earthers about, because flat earthers may say that gravitation isn't far enough away, or the space shuttles aren't far enough away to experience weightlessness, but they actually are not experiencing weightlessness because of no gravity. They're experiencing weightlessness because they are falling around the Earth. Orbital moon and mass. Kepler's law describes the orbits of the object whose motions are described by Newton's laws of motion and the laws of gravity. Knowing that gravity is the force that attracts planets towards the sun, however, allows Newton to rethink Kepler's third law. Recall that Kepler had found a relationship between the orbital period of the planet's revolution and its distance from the sun, but Newton's formulation produced the additional force of the mass of the sun, m1, and the planet, m2, both expressed in the units of the sun's mass. Newton's universal law of gravitation can be used to show mathematically the relationship is a cubed equals m1 plus m2 times p squared, where a is the semi-major axis and p is the orbital period. How did Kepler miss this factor? In the units of the sun's mass, the mass of the sun is 1, and in the units of the sun's mass, the mass of the typical planet is negligibly small factor. This means that the sum of the sun's mass and planet's mass is very close to 1. This makes Newton's formula appear almost the same as Kepler's. The tiny mass of the planets compared to the sun is the reason that Kepler did not realize that both masses had to be included in the calculation. There are many situations in astronomy, however, in which we do need to include two masses terms. For example, when two stars and two galaxies orbit each other. Including the mass term also us to use the formula in a new way. If we can measure the motions, distances, and other periods of objects acting under their mutual gravity, then the formula will permit us to deduce their masses. For example, we can calculate the mass of the sun by using the distance and orbital period of the planet, or the mass of Jupiter by noting the motions of its moon. Indeed, Newton's reformulation of Kepler's third law is one of the most powerful concepts in astronomy. Our ability to deduce the masses of objects from the motion is key to understanding the nature and evolution of many astronomical bodies. We will use this law repeatedly throughout this text and calculation that ranges from orbits of comets to the interactions of galaxies. So the point is, these mathematical equations explain observable phenomenon, right? They observe, yes, they explain observable phenomenon, and they eventually are going to be used to make predictions. So these things do make sense, right? Give me 1 second. Let me just see something. I just want to make sure I posted something. Hold on. Okay. Hold on. Let's see how long this one is. Okay, short one. Okay, orbits of the solar system. Recall in the path of an object under the influence of gravity through space is called its orbit. Whether that object is a spacecraft, planet, star, or galaxy, an orbit once determined allows the future position of the object to be calculated. Two positions in any orbit in our solar system have been given special names. The place where the planet is close to the sun, Helios in Greek, and moves the fastest is called the perihelion, and its orbit and its orbit, and the place where it is the farthest away moves the most slowly in aphelion. For the moon or a satellite orbiting Earth, the corresponding terms are perigee and apogee. In this book, we use the term moon for a natural object that goes around a planet, and the word satellite to mean a human object orbiting that revolves around the planet. Orbits of the planets. Today, Newton's work enables us to calculate and predict the orbits of the planets with marvelous precision. We know either 8 planets, beginning with Mercury closest to the sun and extending out towards Neptune. The average orbital data for the planets are summarized in table 3.2. According to Kepler's law, Mercury must have the shortest orbital, 88 Earth days. Thus, it has the highest orbital speed, average 48 kilometers per second. At the opposite extreme, Neptune has a period of 165 years and average orbital speed of just 5 kilometers per second. All of the planets have orbits of rather low eccentricity. The most eccentric orbit is that of Mercury, 0.21. The rest have eccentricity smaller than 0.1. It is fortunate that most of the rest, Mars and an eccentricity greater than that of many of the other planets. Otherwise, the pre-telescopic observations of Brocky could not have been sufficient for Kepler to deduce that its orbits had shapes of an ellipse rather than a circle. The planetary orbits are also confined close to the common planet, which is near the plane of Earth's orbit, called the elliptic. The strange orbit of the dwarf planet Pluto is inclined about 17% to the elliptic, and that of the dwarf planet Eris, orbiting even further away from the sun than Pluto, by 44%. But all the major planets lie within 10 degrees of the common plane of the solar system. Orbits of asteroids and comets. In addition, the 8 planets, there are many smaller objects in the solar system. Some of these are moons, natural satellites that orbit all the planets except Mercury and Venus. In addition, there are 2 classes of small objects in heliocentric orbit, asteroids and comets. Both asteroids and comets also believed by small chunks of material left over the formulation of a process of solar system. In general, asteroids have orbits with smaller semi-major axes than comets. The majority of them lie between 2.2 and 3.3 AU in the region known as the asteroid belt. As you can see, the asteroid belt represented by the larger member Ceres as in the middle of a gap between the orbits of Mars and Jupiter. It is because these 2 planets are so far away, the stable orbits of small bodies can exist in the region between them. Okay, so here it's just showing us the planet circling. It does look like circles, but they are eccentric. And here's the eccentricities of them. Eccentricities. Comets generally have orbits of larger size and greater eccentricity than those of asteroids. Typically, the eccentricity of the orbit is 0.8 or higher, according to Kepler's second law. Therefore, they spend most of their time far from sun, moving very slowly. As they approach perihelion, the comets speed up and whip through the inner parts of the orbit rapidly. Okay. Okay, we have 2 more sections to go for today. Okay, this one is called, just give me a second, let me see something. Nobody's watching, but that's fine. Somebody is watching, at least now. At least somebody's watching, so let me continue. Last one was about an hour. This one will be about an hour too. So let's continue. Newton's universal, so this is motion of satellites in spacecraft. Give me one more second. Newton's universal law of gravitation and Kepler's law describes the motion of Earth's satellite and interplanetary spacecraft, as well as the planet. Sputnik, the first artificial satellite, was launched by what was then called the Soviet Union on October 4th, 1957. Since the time, thousands of satellites have been placed into orbit around Earth, and spacecraft have also orbited the Moon, Venus, Mars, Jupiter, Saturn, and numbers of asteroids and comets. Once an artificial satellite is an object, its behavior is no different from that of a natural satellite, such as our moon. If the satellite is higher enough to be free of atmosphere friction, it will remain in orbit, however, forever. However, although there is no difficulty in maintaining a satellite once it is in orbit, a great deal of energy is required to lift the spacecraft off Earth and accelerate it to orbital speed. To illustrate how the satellite is launched, imagine a gun firing a bullet horizontally from the top of a high mountain, as in figure 311, which has been adopted from a singular diagram by Newton. Imagine further that the friction of the Earth could be removed and nothing gets in the bullet's way. Then the only force that acts on the bullet after it leaves the muzzle is the gravitational force between the Earth and the bullet. If the bullet is fired with a velocity we can call VA, the gravitational force acting upon it pulls it down toward Earth, where it strikes the ground at point A. However, if given a higher muzzle velocity, VB, its higher speed carries it farther before it hits the ground at B. Okay, so I guess if our bullet is given a high enough muzzle velocity, VC, the curved surface of the Earth causes the ground to remain the same distance from the bullet, so that the bullet falls around Earth in a complete circle. The speed needed to do this, called the circular satellite velocity, is about 8 kilometers per second, or about 17,500 miles per hour in more similar orbits. Interplanetary spacecraft. Okay, so here's this gun. Okay. Here we go. If it's going fast enough, it'll go around the Earth. I guess if you shoot this gun. Okay. Interplanetary spacecraft. The exploration of the solar system has been carried out largely by robot spacecraft sent to the other planets. To escape Earth, their craft must achieve escape speed. The speed needed to move away from the Earth, however, forever, which is about 1.1 kilometers per second, about 2,500 miles per hour. After escaping Earth, the craft coasts to their target, subject only to minor trajectory adjustments provided by small thruster rockets on board. In interplanetary flight, these spacecraft allow orbits around the sun that are modified only when they pass each other near one as the planet. As it comes close to the target, a spacecraft is deflected by the planet's gravitational force into a modified orbit, either gaining or losing energy in the process. Spacecraft controllers have actually been able to use the planet's gravity to redirect flyby spacecraft to a second target. By example, Voyage 2 used a series of gravitational assisted encounters to yield successive flybys of Jupiter 1979, Saturn 1980, Uranus 1986, and Neptune 1989. Galileo's spacecraft launched in 1889 flew past Venus, once the Earth, twice to gain the energy required to reach its ultimate goal of Jupiter. If we wish to orbit a planet, we must slow the spacecraft with a rocket when the spacecraft is near its destination, allowing it to be captured in an elliptical orbit. Additional rockets thrust it required to bring a vehicle down from orbit to land on the Earth. Finally, if a return trip to planet is planned, the landed payload must include enough propulsive power to repeat the entire process in reverse. So, okay, launching of satellites. I mean, so the flat earthers are saying satellites don't exist. That's their only example, right? But I mean, so if you believe we're launching satellites or satellite TV or satellite phone or anything like that, I guess that a lot of flat earthers would say that this is a conspiracy theory. They would have to make up a reason why the satellites aren't falling towards flat Earth. Whereas if we have a round Earth, global Earth, then we can explain these things and we can believe that satellites are real. You know, satellites are real, birds are real. Gandalf says that Juvit has been arrested by the police. I doubt that. What would he be arrested by the police for? Okay, gravity with more than two bodies. Okay, let's finish this and then I'm done for today. And then we're going to move on to Earth, Moon, and Sky. Until now, we have considered the sun and the planet, or planets and one of the moons, as nothing more than a pair of bodies revolving around each other. In fact, all planets exert gravitational force upon one another as well. These interplanetary attractions cause light variations from the orbit that would be expected if the gravitational force between planets was neglected. The motion of a body that is under the gravitational influence of two or more other bodies is very complicated and can be calculated properly only using with large computers. Fortunately, astronomers have such computers at their disposal and universities and government research institutes. The interaction of many bodies. As an example, suppose you have a cluster of 1,000 stars all orbiting a common center. Such clusters are quite common, as we shall see in star clusters. If we know the exact position of each star at any given instance, we can calculate the combined gravitational force of the entire group on any one member of the cluster. Now, knowing the force on the star in question, we can therefore find how it will accelerate. If we know how it was moving to begin with, we can then calculate how it will move in the next instant of time, thus tracking its motion. However, the problem is complicated by the fact that the other stars are also moving and thus changing the effect they will have on our star. Therefore, we must simulate calculations that accelerate each star proportion to the combination of gravitational attraction of all the others in order to track the motion of all of them and hence of any one. Such complex calculations have been carried out with modern computers to track the evolution of hypothetical clusters of stars with up to 1 million members. Okay, so stars move in the way that they're supposed to based on their gravitational and elliptical orbits. Okay, that's why we can tell where all the stars are going to be. The interaction of many bodies. Wait. Within the solar system, the problem of computing the orbits of planets and spacecraft is somewhat simpler. We have seen that Kepler's law, which do not make into account the gravitational effects of the planets on an orbit, really work quite well. This is because the additional influences are very small in comparison with the dominant gravitational attraction of the sun. Under such circumstances, it is possible to treat the effects of other bodies as small perturbations or disturbances. During the 18th and 19th centuries, mathematicians developed many elegant techniques for calculating perturbations, permitting them to predict many precisely the position of the planet. Such calculations eventually led to predictions and discoveries of planets in 1846. So how are we able to predict all of these planetary phenomenon and movements if this is not what's happening in the sky? The discovery of Neptune, the discovery of the 8 planets. Neptune was one of the higher points In the development of gravitational theory in 1781, William Herschel, a musician and amateur astronomer, accidentally discovered the seventh planet, Uranus. It happens that Uranus had been observed a century before, but in none of these earlier sightings was it recognized as a planet. Rather, it was simply reported as a star. Herschel's discovery shows that there could be planets in the solar system too dim to be visible with the unaided eye, but ready to be discovered with a telescope if we just knew where to look. In 1790, an orbit had been calculated for Uranus using observations of its motion in the decade following its discovery. Even after allowance was made for the perturbation effect of Jupiter and Saturn, however, it was found that Uranus did not move on an orbit that exactly fit the earlier observations of it made since 1690. By 1840, the discrepancy between the position observed by Uranus and those predicted from its computed orbit amounted to about 0.03% degrees, an angle barely discernible to the unaided eye, but still larger than the probable errors in the orbital calculations. In other words, Uranus just did not seem to come on the orbit predicted from Newton's theory. In 1843, John Couch Adams, a young Englishman who had just completed his studies at Cambridge, began a detailed mathematical analysis of the irregularities in the motions of Uranus to see whether they might be produced by the pull of an unknown planet. He hypothesized a planet more distant from the sun than Uranus, and then determined the mass of the orbit it had to have to account for the departures of Uranus's orbit. In October 1845, Adams delivered his result to George Airy, the British Astronomer Royal, informing him that where in the sky to find the new planet. We now know that Adams' predicted position of the new planet was correct within 2 degrees, but for a variety of reasons, Airy did not follow up right away. So this must be Neptune that's coming in. Okay, so we can predict that there's another planet out there before we even see it, based on these elliptical orbits and everything going around the sun and having gravitational pull towards each other. Meanwhile, French mathematician Urbain Jean-Joseph Leverrier, unaware of Adams or his work, attacked the same problem and published a solution in 1846. Airy, noting that Leverrier's predicted position for the unknown planet agreed within 1% with that of Adams, suggested to James Callis, director of the Cambridge Observatory, that he begin a search for the new object. The Cambridge astronomer, having no up-to-date star charts of the Aquarius region of the sky where the planet was predicted to be, proceeded by recording the positions of the faint stars he could observe with his telescope in that location. It was Challis' plan to repeat such plots of intervals of several days, in that hopes that the planet would distinguish itself from stars by its motion. Unfortunately, he was negligent in examining his observations. Although he had actually seen the planet, he did not recognize it. About a month later, Leverrier suggested to Johannes Galle, an astronomer of the Berlin Observatory, that he look for the planet. Galle received Leverrier's letter on September 23rd, 1846, and possessing new charts of the Aquarius region, found and identified the planet the very night. It was less than a degree from the position of Leverrier predicted. The discovery of either planet, now known as Neptune, the Latin name for the god or the sea, was a major triumph for the gravitational theory, for it dramatically confirmed the generally of Newton's law. The honor of its discovery is properly shared by the two mathematicians Adam and Verrier. Okay, so due to all this, okay, the Uranus still goes around the sun, but we knew there was another planet going around the sun even before we found it. We should note that the discovery of Neptune was not a complete surprise to astronomers who had long suspected the existence of the planet based on disobedient motions of Uranus. On September 10th, 1846, 2 weeks after Neptune was actually found, John Herschel, son of the discoverers of Uranus, marked in speech before the British Association, "We see the new planet as Columbus saw America from the shores of Spain. Its movements have been felt trembling along the far-reaching line of our analysis with a certainly hardly inferior to ocular demonstration. This discovery was a major step forward in combining Newton's theory with painstaking observations. Such work continues in our time with the discovery of planets and other stars. Okay, so they said it's going in an elliptical orbit. They said that the other planet around it is going in an elliptical orbit. And with these calculations, assuming that this all goes according, this all works. If we put everything in our model, it all works. Okay, so this is our evidence. Every observable phenomenon in the sky makes sense if this is our model. So why does the model work so well if it's not true? Why does it follow all these precise laws if it's not true? Okay, that's enough for today. We're going to continue tomorrow. Have a good day. Bye.